Hey, this is Chapter 9. We're going to combine sections 1 and 2 together and work on stoichiometry. You do need your calculator and a periodic table handy as we go through these calculations. So starting off, just a couple definitions. What is stoichiometry? It is the mass relationship between substances in a chemical reaction. It is based on the mole ratio, and for a mole ratio, we have to have a balanced chemical reaction. A mole ratio, we use the coefficients in the balanced equation. These numbers out front, so in this one it's 2 and understood 1 and 2 are the coefficients. And we can change those ratios however we want to do this. It just depends on the two substances in question. In this reaction, I could compare magnesium to oxygen, oxygen to magnesium oxide to magnesium, and then flip any of those three that I just stated. So there would be 6 possible mole ratios depending on the question at hand. So, stoichiometry, get into those steps. Step number 1, you have to write a balanced equation. We've either done it earlier in this school year or you did it during, or if this is Chem 2, you did it during Chem 1. So we're writing a balanced equation first, so those coefficients that go out front of each substance. You will identify your known and unknown. The known and unknown, I will explain further once we get into our different problems. And at that point, we line up conversion factors. So here in this chapter are some conversion factors that you might see. First off, a mole ratio is converting moles to moles. There is a mole ratio step in every single problem that we're going to do. Next, molar mass could be involved. That's where you convert between moles and grams. Molarity is a new one for you. That's the concentration of a liquid substance. So we're comparing moles and liters of solution. And then molar volume, where you compare moles and liters of a gas. So molar volume deals with a gas, molarity deals with a liquid. And the core step in all of these is your mole ratio, and we'll check our answer. Now I'm going to go to another slide, and I'm going to break down these 4 that we've just talked about so that you can see within our conversion, so we're going to be setting up grids, where these units may or may not fall. So starting off with the mole ratio, I'll try to color code some of this stuff. Maybe we can stick with the color coding as we go through. Mole ratio. Moles and moles are in the numerator and denominator. Moles of your known substance are always in the denominator of your mole ratio step. Moles of your unknown substance will always be in the numerator. The numbers that are going to go out front, because we got to have some values that go into here, these are the coefficients. So within your balanced equation, the coefficient that is in front of your known and unknown substance, that's where those values are used. So that's during your mole ratio step. The next one we're going to look at was the molar mass. And you should be used to using molar mass by now, but the traditional units for molar mass are grams per mole. And it's understood grams per 1 mole of a substance. And the number that is going to go with grams will be found on the periodic table. It'll be found on the periodic table. If it's just an element, great. You find the mass on the periodic table. If it's a compound, you'll have to calculate the molar mass of the entire compound, and then that number goes with grams. The 1 always goes with moles. The next one mentioned was molarity. Molarity. This is also called molar sometimes, especially if you have the number first. So like 4 molar or 6 molar, talking about the concentration of your substance. If it comes after a number, you will see molarity used the abbreviation of a capital M. The official units for molarity are going to be moles per liter, and it is understood per 1 liter. And this is a solution, so you have to be dealing with something in liquid form to use this. And the moles part is typically given within the problem. It's either given within the problem, so molarity, it might be 4 molar, so that's 4 moles per 1 liter, or it is something you would be solving for. And then the last one we're going to deal with in this chapter is going to be molar volume. Molar volume deals with a gas, and the units for it also deal in mole and liters, but this time liters is in the numerator, moles is in the denominator, and it is so many liters per 1 mole. We will, in the next, maybe a couple chapters away from now, we're going to get into gases and their properties and calculations with gases. And this 22.4 will be a number that will show up again. So that number, if you have to use molar volume dealing with a gas, it is going to always be, for ideal gases, which is what we'll do in this chapter, 22.4 liters per 1 mole. So again, make sure you get this stuff written down. So here's that 22.4 again. For a gas, in this chapter, we're going to work at STP. That is standard temperature and pressure. So standard temperature is 0 degrees Celsius or 273 Kelvin. Standard pressure is going to be 1 atmosphere. So if you have an ideal gas at that temperature and pressure, it will take up a volume of 22.4 liters based on 1 mole of that substance. Here's also another way of writing what we just did. Back in chapter 7, we had everything right across the middle. So all of that hopefully looks familiar from chapter 7. And in this chapter, we're going to mainly be dealing with this area right in through here. Again, it's just another way of showing you what we were working with. And we're going to throw up some of the information there. Molar mass is the conversion needed between mass and moles. Again, because I see grams for mass, moles for moles. We're not going to deal with particles in this chapter, but molarity, that's between liters of solution and moles. Again, there's your mole and liter. And then for a gas, we're going to deal with molar volume, and there's that 22.4. Now, for all of these units, when I had it up earlier, the only one that cannot flip is mole ratio. Mole ratio is always moles of known in the denominator, moles of unknown in the numerator. The other 3 could easily flip. Their numbers flip with the units. So you will always see me highlighting units and where they go. So in this example right here, write down the example. We're going to go work it out on a separate slide. How many moles of potassium chlorate must decompose in order to produce 9 moles of oxygen gas? You need a balanced equation for this. Back in what you should have had in Chapter 8, probably from Chem 1 if you're in Chem 2 now, it says KClO3 decomposes, and when it decomposes, it will decompose into potassium chloride and oxygen. You should recognize that as oxygen gas, so it's in its gas phase. Now we have to go back and balance it. So just a real quick refresher on balancing. I see a polyatomic ion there, but it is not still a polyatomic ion on the right side. So we're going to break it down into potassium, chlorine, and oxygen. On the left, 1 potassium, on the right 1. Chlorine, on the left 1, on the right 1. Oxygen, on the left we have 3, and on the right we have 2. Oxygen's out of balance. On the right side, I would normally say, hey, just go straight. Just bump up your coefficient of 1 to a 2. And again, the coefficient is going to be right over here. But I know that with what we have going on each side, I can go ahead and go straight to 3. So for oxygen, 3 times 2 is 6. And on the right side, I need to bump up oxygen there. I'm going to go ahead and put a 2. So that changes oxygen to 6. It also changes potassium and chlorine, each to 2 atoms. So when I go back to the right side, the potassium and the chlorine need to be bumped up, so their coefficient changes to a 2, and everything is balanced below that. I'm going to go and erase that part. And again, there are our coefficients that we have. So 2, 2, and 3. The question was, how many moles of potassium chlorate? So I'm going to put a question mark there. I'm looking for moles. Must decompose to produce 9 moles of oxygen gas. So the 9 moles of oxygen, 9 moles goes underneath oxygen. I set up a grid. Please get used to setting up a grid if you are new to this. Our given always goes into the grid first. So your given information always goes in first. Well, the given, that's the only number that is numerically given here. So I'm going to put the 9 moles of O2 in there. Notice, I'm not skipping any part of this. I've put a number, I've put a unit, and I've labeled the substance. And I would expect that you would do the same thing. A number, a unit, and label your substance. In stoichiometry, for everything we're going to do, whatever unit and label you have here gets repeated there in the denominator, because that is not what we want in our answer. So I'm going to go over there and repeat moles of oxygen in the denominator. So what goes in the numerator? Well, from the previous slide that I had added, that's moles of our known substance. We know something about it. So we automatically do the mole ratio step here. Moles of unknown goes on top. Our unknown is where that question mark is at, KClO3. And since we're going to moles, that's great because that's what we're actually looking for. Again, if you go back, you have to put some numbers in here. During the mole ratio step, that's where we add our coefficients. So the coefficient in front of KClO3 is 2. The coefficient in front of oxygen is 3. That's where we finally use the coefficient. Moles of O2 cancels. That's great. I'm left with moles of KClO3, and the problem asked us to find that. And you are ready to calculate. Everything above this long divide line is multiplied. Anything below it is divided. So that's just like saying 9 times 2 divided by 3, which is 6. So your final answer is 6 moles of potassium chlorate. Again, mole ratio step is in every problem. It might not be the first step. I don't ever count the given as a step. That right there is considered the first step to me. And we're going to have some problems that are going to be multiple steps. Okay, write down this question. How many grams of potassium chlorate are required to produce 9 liters of oxygen at STP? Same equation as we had earlier, but our information is a little bit different. So I'm going to go ahead and rewrite that balanced equation that we had. Put in our coefficients from when we balanced it, which were 2, 2, and 3. Now I'm going to label the information that was given. This time they want to know how many grams of potassium chlorate are produced from 9 liters of oxygen gas at STP. So when we set up our grid, given information goes in first. That is what is given, 9 liters of oxygen. Again, label, 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 units, and whatever the substance is. The unit and the substance have to be repeated down there because we don't want that in our final answer. So that is liters of O2. Well, when I look back at those boxes, liters has to go to some other unit. The only unit it can go to, and this is what I'm thinking of whenever I'm looking at that. We had molarity down here. We had molar volume up here. We had moles in the middle. We had grams over here. That's how this works. Everything has to go through moles, but there's not a direct connection between grams and liters. So if I have liters of O2, I know that liters has to go to moles of O2. Now I have two different scenarios that use liters and moles. This one at the top was molar volume for gases. At the bottom is molarity for liquids. Make up your mind which one we're using. The question says 9 liters of oxygen at STP. The STP is a giveaway that you're dealing with a gas. So we have to go to that information dealing with the gas. And the information that we had dealing with the gas was 22.4 liters per 1 mole. Notice the units are flipped here. That is totally fine that they are flipped. That 22.4 has to go with liters, and the understood one is going with moles. These units cancel. I'm left with moles of oxygen. That's not what we're looking for, so we have to add another step. Again, moles of O2 has to be repeated right down here. Moles of O2. That should set off going, oh, moles of known is in the denominator, so moles of unknown has to go in the numerator. My unknown is where the question mark's at, KClO3. And this is the step where you use your coefficients. So 2 and 3. Mark that out. I'm left with moles of KClO3, but it's asking for grams of KClO3, which means, yes, another step. So when I go back and I look at this, moles of KClO3 has to be repeated right down there again so that they can cancel. That's moles of unknown, but I can go from moles of unknown over to grams in that one step. So I am right in here. So I'm going to put grams up above there, which is great because that's what we're looking for. And you should remember from all of these boxes the grams per mole. We get the the grams from the periodic table. So you've got to go calculate the mass of KClO3 from the periodic table. You have 1 potassium, 1 chlorine, 3 oxygens, and when you go find the mass of each of these off the periodic table, I see 39.10, 35.45, 16. Do your math there, add it all up, and your final mass for these should be 122.55 grams of KClO3, and that is per 1 mole because that's where the 1 is understood. It's based on the definition for molar mass. Now we're ready to do our final calculation. Again, everything above that long divide line, 9 times 1 times 2 times 122.55, divide by 22.4, divide that by 3, divide by 1. Your final answer is 32.8 grams of KClO3. Please make sure you can put this into your calculator properly. On to the next problem. How many grams of silver will be formed from 12 grams of copper? Now this question does not give you enough information to write out the balanced equation, so I'm going to go ahead and give you the balanced equation, and then we will work through the problem itself. So this is supposed to be based on copper reacting with silver nitrate to produce silver and copper to nitrate. Please refresh yourself on how to do balanced equations. I'm going to go ahead and give you the coefficients. They are 1, 2, 2 and 1, you don't actually write the 1 as a coefficient. In the problem, the question said how many grams of silver? So underneath silver, we're going to put a question mark in grams. Can be produced from 12 grams of copper. Again, our given information goes into the grid first. Given is 12 grams of copper. Now, that has to be repeated right down there. And we're going to grams of copper. Now, with my boxes, it looks like everything is right in here. So we're going from grams to moles first. That's great. That is molar mass, just the units are flipped upside down. It's still the mass from the periodic table based on 1 mole. So copper's mass from the periodic table is 63.55. 63.55. Those units cancel. So I'll rock on because I don't want moles of copper in my final answer. Moles of copper has to go down here since we want these units and substance to match up so that they can cancel. That is moles of known in the denominator, so moles of unknown have to go in the numerator, and this is where we add our coefficients. So copper is an understood 1, silver is 2. Those units cancel. I'm left with moles of silver, but guess what? Yes, we went from grams to moles. While you're there, do a mole ratio step, but now we've got to go back to grams again. So we're going back to grams again. So extend out our grid. Moles of silver, we don't want that in our answer. I'm just looking for a different color. So it's repeated right down there. Moles of silver. And we can go from moles back to grams. It's still molar mass. This time it's the molar mass of silver. It's based on 1 mole. So you go back to the periodic table, find your silver, and silver's mass is 107.9. Those units cancel. You are ready to do your math since we have grams of silver. And 12 times 1 times 2 times 107.9 divide by 63.55, divide by 1, and your final answer is 40.7 grams of silver. Now, I hope y'all realize you don't actually have to put into your calculator, multiply by 1 or divide by 1 because that will not change your answer. But I am showing you how the math works in the grid. Let's go do one more problem. We're going to deal with the same reaction. This time, how many grams of copper are required to react with 1.5 liters of 0.1 molar silver nitrate? So get that question written down and let's go work it out. So this one's a little different. We are looking for grams of copper, but it gives us 2 pieces of information about silver nitrate. It says we have 1.5 liters of silver nitrate, and the capital M for molarity also goes under silver nitrate, but within our grid, you're not going to see a capital M, but you would see the units for molarity. So the first thing I would do is change that capital M to the units it actually represents, which are moles per 1 liter. Those are the units for molarity. Now we're ready to get started. I've said start with the given. Since we have 2 pieces of given information, and I know liters does not need to be in our final answer, I'm going to tell you, go go ahead and start with the number that has 1 unit associated with it, which is liters. And there's your 1.5 liters of silver nitrate. So yeah, we're going to have a lot of labeling going on, but that's okay. That unit and label needs to be put in the denominator so we can get rid of it. And based on all those boxes, you can go from liters to moles. Liters to moles. So go back and look at your boxes. Those happen to be the units for molarity. So we're not dealing with molar volume here. All the problems we're going to do in this chapter, I will either, if liters is mentioned, it will either be molar volume or molarity. I will not give you a problem that deals with both in the same problem. So this one is definitely molarity because we had the capital M. We're dealing with a solution, not a gas. Here's the values for what we're looking at right here. The 0.1 and the 1. The 1 goes with liters. The 0.1 goes with moles. Cancels. And now we are ready for the next step because I don't want moles of silver nitrate in my answer. That has to be duplicated here at the bottom. That is moles of your known, so we have to go to moles of unknown. Unknown's where your question mark is at, and put your coefficients. The coefficient for copper is an understood 1. For silver nitrate, it is a 2. The units cancel. We're left with moles of copper. The question wants us to find grams of copper, so we've got to continue to move on. And these units that you see right here for moles will get recreated there at the bottom. And you can go from moles to mass. Again, I'm thinking of the boxes in my head as I go through that. So moles to mass, that's molar mass. Go to the periodic table and find the molar mass of copper. It is 63.55, and that has to go with grams. Understood, 1 goes with the moles. These units cancel. I'm left with grams of copper. That's great because that's the unit that we're looking for. So 1.5 times 0.1 times 1 times 63.55 divide by 1, divide by 2, divide by 1. Your final answer is 4.8 grams of copper. Please, when you're doing your homework, set up a grid, show your balanced equation, show all of your work. Do not skimp on any labels, any units, any work.